Okay, in this lecture we're going to talk about finding zeros, and we start off by borrowing a technique we had from quadratic polynomials, degree 2 polynomials. You remember had this form. Now if we wanted to factor this, then what we said was we could use what's called the AC method. In other words, we looked for factors of AC that add to B. Now we're going to borrow this type of method, and we're going to apply it to higher degree polynomials, but they must have integer coefficients. So make sure you understand what an integer means, right? And that means, of course, that we need to have whole numbers, positive or negative. All right. All right. And so consequently we need to also identify that first before we can actually apply this method. And the method actually says this, that if P over Q is a rational number, which we've written in lowest terms, and if this P over Q is a zero of a polynomial, F, right, that has these integer coefficients, then P is a factor of the constant term and Q is a factor of the leading term. And you remember that a polynomial could be written like this. This is an nth degree polynomial. And we went all the way down here to x2 x squared. Right, so this one here is the constant term. And of course this one up here is in fact the leading coefficient. So what this is saying is that I can start to look at all the rational numbers formed by P over Q, where P, of course, comes from the constant term, and Q is coming from the leading coefficient. Right, well, let's see how this actually works. So let's suppose here's our polynomial, and let's suppose this is f of x is equal to x cubed plus 5x squared plus 2x minus 8. So if we look at this, we're looking at here the leading coefficient is 1 and the constant term is in fact negative 8. So remember, we're looking for Q being a factor of the leading coefficient. So here's Q factors, if you like, and we're looking of them for 1. Of course, it's only plus or minus 1 are the possible factors of 1. Right, so next, of course, because negative 1 by negative 1 is 1, and of course 1 by 1 is 1. And for the constant term, we're looking for P factors. Right, and that is going to be of negative 8, of course, is going to be plus or minus 1, divides into negative 8, plus or minus 2, all right, plus or minus 4, and of course plus or minus 8. So consequently, we are therefore looking for the P over Q possibilities, and the P over Q possibilities will be 1 over 1. So if you like, plus or minus 1 over plus or minus 1, right, which of course is plus or minus 1. We could have plus or minus 2 over plus or minus 1. All right, and this is going to produce plus or minus 2. And we have plus or minus 4 on plus or minus 1. Which gives us plus or minus 4, and same with 8, plus or minus 8 over plus or minus 1. So it's good if we only have a 1 in front of the leading term, and that'll be plus or minus 8. So these are the ones that we have to look for. And so we start with the first one, and we say, all right, let's do a quick synthetic division. So we have a 1, we have a 5, we have a 2, and we have a negative 8. if I put a 1 in here, bring down a 1. 1 is 1, so that gives me 6. And 1 6 is 6 plus 2 is 8. And this gives me 8. And we've been fortunate that we've found it on the first turn. So in other words, this tells me that in fact x minus 1 is a factor, and it tells me that 1 is a 0. Right, so now, of course, we have x squared plus 6x plus 8 is our remaining quadratic here. And of course, we're looking for these being equal to 0. Okay, so we're looking this to be equal to 0. And therefore, we will have x by x, and we'll have a 4 and a 2. And they'll be plus 4 and plus 2. And you'll notice that these also are showing up here and here. Okay, so we did find all the possibilities here, and we know that the zeros are in some of those possibilities. Alright, and so this will tell me that the zeros, alright, are in fact 1, -2, and -4. And the factors, of course, if I want to factor f of x, right, this will become x take 1 by x plus 2 by x plus 4. And that's our factored form. Right, so again, the rational zeros theorem tells us all the possibilities to look into. Now, there can be a large number of possibilities, but that's certainly better than trying every number that exists. Okay, so in the next one we have a very important result, which is the fundamental theorem of algebra. And this says that every function defined by a polynomial of degree 1 or more has at least one complex zero. Now remember, a complex number, alright, is a number of the form a plus bi. And remember that a real number is a complex number. It's just that the b part is 0. So that includes real numbers, but not every complex number is a real number, alright, because if a was 0, then we'd have an imaginary number, which is complex, alright, but is imaginary. Now, of course, if you look at a picture of this and we look at a straight line, which is a degree 1 polynomial, see here we have one real 0. If we look at a quadratic, we could have a quadratic like this where it touches. Right, so it has one 0, but one distinct 0, but there's two equal ones. And of course, we could have a one like this, right, in which we have two real ones and they're distinct. Or we could have something like this, where it doesn't cross the x-axis, so we don't have any real ones, but we have at least one complex one. And so forth as we go up with different degrees of polynomials. But this is really saying that every function defined by a polynomial of degree 1 or more will have at least one complex 0. And this leads us to what's called the number of zeros theorem. And the function then, which is a polynomial, which has degree n, alright, has at most n distinct zeros. So it can't have more than the number of the degree of distinct, meaning distinct means different zeros. Right, so that means, of course, that we do have ones that are the same as each other, just like this one here, where it just touches the x-axis. And this leads us to a term called multiplicity, right, because a polynomial can have a 0, alright, that has a certain multiplicity. In other words, it occurs a number of times. The same 0 occurs a number of times. And if you remember, think about the squaring function, here it is here. Right, it touches here at 0, so it has a 0 of 0, right, and it has a multiplicity of 2, right, because, right, it's 2, 0 times 0 squared, right, is still 0. So it's the exponent here that tells us the multiplicity. So if you look at this example here, right, a 0 here, of course, is x equals 0, and it has multiplicity, right, of 2. Okay. If you look at this 0 here, when this is equal to 0, this implies then, of course, that x is equal to -2 plus root 3. And there's only one of them, so it has multiplicity 1. Okay. Now if you look at this one here, 2x take 1 cubed, well this implies that 2x take 1 equals 0. Alright, which implies that x equals a half, and this will have multiplicity 3. Okay. Alright, so we can tell then, once it's in factored form, the multiplicity of the particular 0, and that tells us where it's actually touching the axis, the x-axis. Alright, so this will allow us then to be able to find polynomial functions. So let's suppose we want to find a polynomial function of degree 3 with real coefficients, right? If it has zeros of 2, 3 and 5, notice they're all distinct, right? And we have f of 3 is equal to 6. Okay, so in this case here, of course, if we have zeros of a 0 of 2, then x minus 2 is a factor. So let's write this out as a function of x. If we have a negative 3 as a 0, then x plus 3 is a factor. If I have 5 as a 0, then x take 5 is a factor. Now, of course, we don't know if there's a coefficient in front of the largest exponent, so we'll need to take that into account. So we'll put an a in front there. Alright, so let's suppose this is the general form in factored form for our polynomial of degree 3. X by x by x will give us x to the power of 3, so that's our degree 3. We put an a in here because we don't know whether there'll be a number in front of that x cubed term. But we do know that f of 3 is equal to 6. So in other words, if I put 3 where x is, I should end up with a result of 6. So this tells me, this implies then that a by 3 minus 2 is 1, 3 plus 3 is 6, and 3 minus 5 is negative 2 is equal to 6. So this allows me to find a now. So what I have here is negative 12a equals 6, which implies then that a is equal to 6 on negative 12, which of course is negative a half. And so my polynomial of degree 3 will in fact be negative a half by x take 2 by x plus 3 by x take 5. Now we may want to expand this out, and we'll end up with x squared minus 2x plus 3x is x, and subtract 6 by x take 5, and so this will be negative a half by x cubed plus x squared minus 6x minus 5x squared minus 5x plus 30. And so my function is actually equal to, let's have a look here, it's going to be a half x cubed. Now we have x squareds here. We have x squared minus 5x squared is negative 4x squared, and divided by 2 is negative 2x squared. We have negative x subtract 5x is negative 11x, and divide by 2. And 2's into 30 go 15, and that will be my resulting polynomial.